So in this video, we're going to provide a brief introduction of the concept of voltage within circuit analysis. And before we do that, we need to define a very important modeling concept known as the generic two-terminal circuit element that's depicted over here to the right. So in order to understand why this is important, you kind of need to set yourself in a context that all of the content that we're going to be doing this semester in circuit analysis is really just an approximation of Maxwell's equations that tend to hold under certain scenarios of the physical size of elements and the underlying frequencies of excitation. So under those approximations, what we're basically trying to do is take all of the physical elements that occur in electrical systems around us, such as fuses, bulbs, passive components like resistors, inductors, and capacitors that we'll predominantly focus on in this course, along with active components. And we want to kind of take all of those variety of real things and put them into bins of models, depending upon how they behave at their terminals or points of connection from an electrical perspective. And we'll define what that fundamentally means here in a minute. But a two-terminal model, as we see here and to the right, what that really means is we don't care what's going on the inside. It's just an abstraction. And all that we know is we have 2 points to connect electrical sources to it. And just from a terminology point of view, if these terminals are points of connection, these little dots on the end are often referred to as nodes. And nodes are just points of connection within a circuit. That's another word for them. And they're often labeled by letters, as you see here, node A and node B. And what I mean by abstraction is we're not going to care what's going on the inside. All that we will consider is when we place an electrical excitation across those two terminals of connection, what the actual response is, or how much formally what I'm trying to say that we'll be able to say after the next slide is when you connect a voltage, basically how much current is drawn. So actually, in terms of defining voltage, it's probably intuitive to you that for this generic two-terminal model, current can either enter at A and leave at B, or it can leave at B and exit at A. Because remember, the charge of which is just current, which is just charge in motion, is a conserved quantity. So if it goes in A, it's got to go out of B. So in order to push charge, given the kind of underlying theory of electrodynamics that we spoke about in a previous video, it's probably not surprising to you that there will need to be some work expended in order to drive the current through the terminals. Let's just assume for now from A to B. And when you think about what that actual potential or push that's doing that is fundamentally what the idea of voltage is. So very fundamentally, voltage defined in SI units of volts has 1 volt is defined as a joule per coulomb. So let's kind of look at that ratio and see if we can derive some understanding of physically what that's trying to say. So what that means is if there were a 1 volt potential difference across node A to B, and you were to move 1 coulomb through terminal A to terminal B, that would require 1 joule of work. Well, that's kind of like an abstracted ideal. So let's see if we can get a little bit of intuition just from our ideas of basic mechanics. So if you have an object that has a mass and it's at some elevation relative to the surface of the earth, if you elevate it more, clearly you had to do work, right? And when that phone is elevated to that new height, it has more potential energy than it had at the original height. However, if you were to take maybe a 50-pound dumbbell, something that had a lot more mass to it, and you were to lift it up that same amount, you would have to do more work in that case, and there would be more potential energy, because we know that from a physical perspective, potential energy is not only proportional to elevation, but also mass. So what could you kind of define a quantity that between two different elevations in space describe the potential energy difference for a fixed unit of mass? Maybe say like a kilogram. You could say that between this elevation and this elevation, there's this much potential energy difference per kilogram. That's that same idea of what you're really defining when you talk about a voltage or potential difference between 2 points. It's the amount of energy that would be required to basically move charge up the potential gradient from one point to another. So that's where it gets that joule per coulomb definition. An important thing to know about voltage is if you have a potential difference or a voltage between 2 points, and it's always defined between 2 points, that doesn't necessarily mean there's going to be a current. In order to have a current, you would have to have some conductive medium connected across it. And we know that's true because if you think about the gravitational analogy, as I mentioned, if I have 2 points that are at different potential energies or energy per kilogram, there's not necessarily anything falling down until I put something there. But that potential is always there. It's the idea of a gravitational field. So same thing if you think about a battery that's producing a DC voltage across it, right? There's no current flowing until I actually connect a load to that battery. So note that since voltage is kind of analogous to the idea of energy, and we know from our physics classes that energy is a conserved quantity, when we connect a voltage to some type of arbitrary two-element component, like we see over to the right, and it drives a current through that element, and naturally it's doing work. That work or that energy, which the two are analogous, has to be conserved. So when it goes into that arbitrary component, it will be either converted from electrical energy to another form like heat or light, or it will be stored within the component using some type of reactive device like maybe a capacitor or an inductor. So when you think about the polarity of voltage, as we mentioned previously, voltage is always defined as a potential difference between one point and another. So we have to, when we're marking up a circuit, have some notation when we say, hey, the voltage across these two nodes is 10 volts, for example. Well, which one's at high potential and which one's at low potential? So probably not surprising to you that we're going to use the notations of pluses and minuses to kind of indicate when we're given a voltage value, what's at high potential and what's low potential. So if you focus down here on the bottom, we have this two-terminal element. We have node A, we have node B. Notice that the polarity of the marking shows A at high potential relative to B at low potential. The rated value is 5 volts. That means that node A is 5 volts higher than node B, or there's a 5 volt potential difference across these two. Another way to say it sometimes is to move from B to A, there's 5 volt step up, versus to move from A to B, there's a 5 volt step down. Now notice you can have a convention of polarity like we have at the top here, where node A is denoted as positive and node B is denoted as negative, but the rated value is actually negative 5 volts. So if you think about what that means, it means that A is negative 5 volts higher than B. So really what's going on, a more intuitive way to write it would be to swap the polarity and say that B is 5 volts higher than A. And that's what this equation here is saying on the bottom, is whenever you have a voltage value measured between two nodes, if you just swap your polarity references, the only thing that changes is the underlying sign of the voltage. And I'll show you an example here that I think will make this clearer. You have an arbitrary two-terminal element. We're given that the potential measured from the top to the bottom is 17 volts, and we're asked to measure the potential from the bottom to the top. So hopefully you know the answer is just negative 17 volts, but just to show you a framework of how you could actually set that up, if you notice I actually put alphabetic labels on the nodes of the terminals A and B. So now you can actually call V1, the potential from the top to the bottom, as VAB. And then by contrast, V2 is just going to be the potential from the bottom to the top, or VBA. And remember that formula we have on the slides, VAB and VBA are always just the opposite of one another. So if we know V1, V2 is just going to be the, if we know V1, V2 will just be the opposite. So if V1 is 17 volts, V2 will be negative 17 volts. And kind of a similar ideal here, we have V1 measured from the top to the bottom as minus 2 volts. So if we swap our polarity and measure from the bottom to the top, that will just be 2 volts. So hopefully that makes sense. Voltage is an incredibly important quantity that we'll deal with a lot throughout the remainder of the course.